then it's just equal to nRT over P. N is 10.3048 moles. R, I don't have R memorized for bar, so I'm going to use this one, 0.08206 liters atmosphere per mole Kelvin. And then I'm going to change this to bar, and that is that there are 1.01325 bar per atmosphere. And then T is 298 Kelvin, and then P is 1 bar. Can somebody calculate the volume of gas? Roughly about 250 liters, huh? $255.3? 3312. Okay, we'll just do 255.3 liters of propane. So you just bought 255.3 liters of propane. Now, I'm going to ask you this question. Do you expect this to be fairly accurate? And tell me why. Yes. Yes, it should be fairly accurate, or no? It's going to be inaccurate, this calculation. Because well, it's a gas, so it should be okay. You got to ask yourself is this. Gases deviate from ideal behavior at low temperature. Is this considered low temperature for propane? No, this would be high temperature for propane. And at high pressure. Is this considered high pressure? No. And so I don't think this is going to be that bad of a calculation. I think this is going to be fairly accurate, because under these conditions, I don't really think we're going to deviate much, even though propane is pretty non-ideal, right? And so I would suspect that our ideal gas calc is fine. Now, if I change the temperature, let's say I said, well, you know what, I don't want it at 298 Kelvin. I want it at 100 Kelvin. At 100 Kelvin, do you think this is going to be fairly accurate? No, it's going to be highly inaccurate because at 100 Kelvin, you're going to have liquid. You're not going to have a gas. And so it's not even going to be gas for the most part. There will be some vapor, vapor pressure, vapor evaporation. But I expect it to be fairly accurate. Well, let's prove it because we want to see, how that volume is. And so what we need to do is we need to solve this for volume. Okay. Well, let's do that. Let's solve it for volume. All right, versus the van der Waals. So let's try the van der Waals equation and see. Van der Waals should be more accurate. And so let's see if it's going to be worth the hassle of calculating it using the van der Waals equation. And so calculating using the van der Waals equation, solve that equation for V. 626. Solve it for V. And then you look at the van der Waals equation. Is the van der Waals equation going to be easy to solve for V? I mean, this is V to the negative 2. We have V to the positive 1. What kind of equation is that? I guess we can multiply. If we multiply both sides by V squared, then we get a cubic equation, right? A v cubed. So we might be able to do an av cubed plus whatever b squared plus cv. Get it into that form, but we aren't. And so this equation is going to be a pain to solve, right? I mean, how many of these? Maybe Scott solved a lot of these, but how many of these have you guys solved? In Chem, probably 0, right? And so this is an example of an equation that's a pain. And you get more equations that are pain to solve algebraically in Chem 1B. And so this is the initial start to equations that are pain and take a long time to solve. And so we need to do something to make solving this easier. Some other techniques versus solving it exactly. And so what we're going to do is, rather than solving this for an exact answer, we're going to solve this for an approximate answer, or an answer that's going to be plenty close enough to the number of sig figs that we need. And the way we're going to solve this is by, let's say, this is tough to solve. And so the way we're going to solve this is by using this to get an approximate answer. The method of successive approximations. Which is going to be in Appendix A of your book. It's just one page in Appendix A. And so what is the method of successive approximations? The method of successive approximations is just the guess and check method. You guess and check. And so what we do here is we set it up. Guess and check. And so we got one. I'm not gonna write the units. The units should cancel out, right, to give us the correct units on both sides, because they'll just save us some labor. And so plus A. So I gotta look up A for propane. Oops, where was it? This page, I think. And so looking up A for propane, it's 9.39. 9.39. How many moles did I say? 1, right? I'm trying to keep the numbers simple. So that's going to be 1 squared divided by the volume. Well, I don't know what the volume is. That's what we're trying to solve for. So we got V squared here. All right. V, which is our unknown, minus N. N is just 1. B, we get off the table here. B is 0.0905. So 1 times 0.0905 is equal to nRT. Well, N is 1, R is, shoot, I should have written that down, 0.08206 times, we got to convert atmospheres into bars. So liters atmosphere, so this is going to be 1.01325 over 1 times T. 298 Kelvin. And so what we'll do is we'll just go ahead and simplify this. So we have 9.39 over V squared. Over here, V minus 0.0905 here is equal to, can somebody calculate this? This is just going to be 1 times 0.08206 times 1.01325 times 298. 24, give me more digits. 24.78.
0.778.
Okay, 0.778.
Yeah.
All right. Should be. We might need more, but that'll probably do it right now. All right. So now what we're going to do is we're going to guess a V value and see, when we plug the V value on the left side, does it equal the right side? Or how close to the right side does it equal? And so, what's our first V value that we should guess? 100 liters? 500 liters? 50 liters? The best one is, the first one you should do is use V equals 255 liters. Why? Because this is the one from the ideal gas, right? And so this should be close. You know, and we got it from the ideal. I'm not going to do the point whatever, because that's going to just make the calculation longer. But this will give us an idea, you know, do we have to increase it or decrease it, you know, due to non-ideal conditions. So let's take a look here. And so what you're going to do is you're going to do, what, 9.39 divided by V squared, units per volume in liters, plus 1, times the quantity 255 minus 0.0905, which would be 244 point whatever. Does that equal 24.778? No. Okay, so what does it come out to? And so we just compare the left side to the right side. And the right side here is going to be 24.778. And so that's our target. We want 24.778. And so what do we have? Well, running out of time here, so I don't want to spend too much time on this, so I'm going to do the using spreadsheets is very nice for repetitive calculations like this. And you can actually program, write a little thing for it if you want, but we'll plug in our V here, and then we'll just look at the left side of this equation here. And so the first V we're doing is 255. Let's blow this up. And so the left side was equal to, and just type it in, parentheses, 1 plus 9.39 divided by V squared. Times V minus 0.0905. Wow, maybe I made a mistake. Did I make a mistake in my equation? Minus NB. That's quite a bit off. Much more than I was expecting, so I'll check it later. But we could vary it. So for example, if we went to 245, ooh, that's really off. Versus let's go to 265. Let's see what happens. I must have inputted this wrong then. Oh, I see what I did. Yeah, that's better. All right, so we picked at 255. The target was what? On the right side, we had as our target the 224. Ooh, that's off too. That's way off. 24.778. NRT. Like I'm off, so I gotta find this, but in the meantime, why don't you do your calculation and tell me what you get on the left? You got the same? All right. Maybe our initial was it 25 liters? Was that it? Was it 25 liters earlier? No, it was 255. Yeah, it was 255 liters. I should have done this before. I gotta find out where my mistake is, unless somebody sees it. But basically, let me just tell you what the principle is, since I don't have enough time here. So, basically, we're going to be doing this. We're just going to continue guessing different V values until we get, well, are we ever going to get exact? Probably not. But when is close enough? And so this is, when do you stop guessing? Well, where you would stop guessing is when your volume, let's say, for example, your volume starts exceeding the number of sig figs you're allowed. And so let's say the volume came out to 254.386. And this digit threw it off a little bit. So should you go 254.3864, as your next guess, or maybe 66 as your next guess? And so you start varying this digit here, because that's how how precise we have to get it in order to get the changes that are required. But when you look at this number, are we really going to use that many in terms of liters? No. And so when you start adjusting this, and it's getting to the point where, it's insignificant, the volume changes, but still the match in that case is going to be close enough. The other one we look for is when we look at the left, So for example, the left, we wanted to get it to match. So for example, if the left came out to 24.8, then that's not close enough, right? And so we keep going on the left, so we go 7, 7. And so if, let's say we're allowed 5 sig figs here, we want it to round to 8. So if we go 7, 7, 9, 8, that's really close enough, because this will round to this, right? But if we go to 7, 7, 4, maybe that's not close enough if we're allowed 5 sig figs. It depends on the precision we have over here. Then this rounds to 7, 7, 7, which is not 7, 7, 8. And so depending on the precision that we have, we'll continue guessing. And so if this left doesn't quite match, then we've got to continue with the volumes. But if the volume's starting to get to the point where we're at, this would be the 1,000th, this would be the 10,000th place. If we're getting to the 100,000th place, then maybe we got to stop. Okay, it's close enough, the precision. And so the thing to do is, this is a tough one that we started off on for the guess and check method, but an easy one to visualize the guess and check method would be something like this, where 2x is equal to 6. Can you guess what x is, right? Yeah, without having to, x is 3. And so this is the essential aspect of this method here. So we'll stop here and we'll continue.